Now it's time for Romb Technologies. We have live here Damjan. Damjan is the CEO of Romb. Please, Damjan, just introduce yourself fast and what is Romb doing, and then the presentation is yours, the show is yours. I will interrupt you, okay? So I'm sorry for
Please do.
I just tell you sorry, not right now, because I guess there will be some questions. I will read the questions in the chat and I will answer. I will place to them you in real time. Okay. Otherwise, I will think about some things. Okay.
Sounds good. Thanks a lot.
I put the presentation. Is it fine?
Yeah, please do.
No. No. Yeah. Introduce yourself with a face, and then we put the presentation.
So thank you for the opportunity to be here and to present my company and what we're doing. And thank you to all the people in the audience for attending. I hope it will be interesting. So my name is Damjan Miklic, and I'm the CEO and co-founder of Romb Technologies. The company is a spin-off of the University of Zagreb. So our research group did a lot of years of research, over 20 years, on mobile robotics. And we had the opportunity to work with several vendors in the AGV industry from the actually beginning of the century. That sounds like for a long time. And what we realized was that there was this gap between the technology that was being used in the field and the technology that was available, it was being developed in academia. And this is what became the mission of our company. So to take cutting edge research and bring these new technologies and apply them to improve the industrial processes in material handling.
Okay, so what are we gonna see today? Briefly, just very, very short.
So in short, I will walk you through all the components of our solution for AGV for AGV and AMR navigation.
Okay.
From basic and standard stuff to some stuff that's really not even in the market yet. So
Okay.
We'll go the whole length of our technology stack.
I'm eager to learn.
So I hope I'll be able to accommodate. So what's the challenge of automation, right? When we go, especially when we talk to end users, to companies that are running production facilities or logistics facilities, they always talk about automate. They want to automate. They want to have their processes more streamlined, more efficient, more predictable. And yet today, out of 100 forklifts, still 99 are manual and only one is automated. Maybe this, I found some new data. Maybe you, Alfredo, will have some better info on this, that there is, maybe now it's 3 to 100, but still it's below 5%. And so, and especially so automation seems to be really well established in greenfield projects, in large projects where there is tens of vehicles, fully automated projects, but a lot of brownfield, smaller projects seem to find hard to adopt automation. And so we have identified maybe three main areas where technology can help to ease this adoption. One is modularity. So when you think about the companies that provide automation solutions, these are typically system integrators. A lot of them build their own machines. They also do they do conveyors. They do maybe robotic arms. They make their own AGVs, and they're really good at building things from components and building things that are custom tailored for their customer requirements. So when they have components like you can buy components for mobile robots, wheels, power converters, sensors, but and we were trying to do the same thing with software. We want to provide software components where they can choose the components that they need and they're best suited for the use case, and they can build the rest around themselves, because they typically have capable teams of programmers who are maybe not domain experts in robot navigation, which we are. So we provide them the components to build their solution. And here it's very important to have good interfaces, and robot operating system, ROS, was a really big I would say, revolution there, where it standardized some interfaces. However, some companies and a lot of companies are starting to use them really already for years. There have been systems deployed that are running on ROS, now also ROS2, but some companies still either cannot or for some reason don't want to use them. So for this reason, we also, so all of our software is written as portable C++ libraries that can run on different types of systems, like on Linux, on Unix, on different types of systems. And then we provide different interfaces. You can integrate them as just a library, or through UDP, through ROS, through ROS2, to provide maximum capability for the client to assemble the kind of system that he needs to solve the end user's problem. The second segment is deployment. So deployment is actually the thing that's probably holding back it's holding back a lot of companies, because right now deployment depends on skilled technicians who are capable to efficiently deploy systems. Usually they spend a lot of time on in the field all over the world, maybe sometime for months at a time, and it's just not a lifestyle that a lot of people can support for a long time. So you have a person that's been trained, that you have invested in for 5 years, and then but because of the long hours in the field, at some point they leave, and then you're left with an inexperienced person. So this is really what's holding back a lot of companies. And then the third thing is adaptability. When we talk about these brownfield applications, that especially so a lot of workflows still require some human-robot interaction, and this is usually where there are problems. So I would like to walk you through now our approach to tackling first deployment and then adaptability. So deployment starts with making a map of the environment, right? And so it used to be that you needed reflective markers which need to be installed and tuned and whatever, but now with our software solution, you can just drive the robot around for the environment manually once, and the robot will use the laser scanner data to build a consistent and accurate map of the environment. And in fact, this map can be used immediately for navigation. There is no need to clean the map or to remove some artifacts. It can be used immediately for navigation, and then the robot uses its onboard laser sensor and the wheel encoder, so it fuses this data to localize the robot in real time using just the natural features of the environment.
But Damjan, when you say that it's not necessary to clean, I can imagine that it depends also on the environment, because if you have very net walls or columns, everything, maybe it's true. But if you find many different things, maybe you need to clean somehow. No, how does it work?
That's true. So there are situations where some cleaning may be necessary, but those are so typically if you use the safety laser scanner for localization, and if there is a lot of clutter around, then maybe you would need to do some cleaning. But
you mean the lower one, from the safety one on the floor level?
Exactly, the ones on the floor level. But typically, if you use if for a navigation laser, so far we haven't had a need when you needed cleaning, because the algorithm is quite robust. As long as it sees some fixed landmarks, some fixed features of the environment, it will attach to those and will basically ignore the smaller inconsistencies.
So in case we are just using the upper LiDAR, okay, theoretically it's not necessary to clean the map anymore. So the result of the first initial mapping is already good for navigation.
Exactly, that's right. That's exactly.
Okay.
And this was a small environment. We're still a small company, so our testing area is a small hole. But the biggest space we did is 240 by 250 meters, so 60,000 square meters. And this was an especially difficult case because it had a lot of windows and just columns, very few features. So this is but this is, let's say, we have tested on this size of environment and it works. So the next important thing for the accuracy and efficiency of the system is calibration. So the accuracy of the system depends on the mechanical construction, let's say where you mount the laser, and the laser is never going to be mounted perfectly. So you need to have a way to but even a centimeter of error in laser mounting, or maybe half a degree of error, will cause problems when the vehicle needs to position itself. So, and this is something that typically people in the field spend a lot of time doing, calibrating. And you could calibrate in the factory, but typically the navigation laser is dismounted for transportation, and once you mount it, it's never going to be mounted perfectly. So this is something you need to do, and for this we have developed an automated calibration procedure, so it doesn't depend on the skill of the operator anymore, and doesn't require him to do this tedious procedure where he needs to be focused for a long time, but the vehicle just does some maneuvers, and based on these maneuvers it automatically calculates the laser pose, also the parameters of the wheel, so if there is some offset of the steering, etc. All of this based on the maneuvers is calculated automatically, and you can put 5 or 10 vehicles to calibrate at the same time, and they will do it in parallel. So one people can calibrate instead of spending up to an hour to calibrate the vehicle, they can do it. You can do, and this procedure takes about 10 minutes for the whole to do all the maneuvers.
Okay.
After we,
one question, excuse me, because you said, imagine that I'm importing a vehicle with your system. Okay, I'm going to install it. You said you remove the navigation because it's very costly, and then the transportation is a disaster. Always, I know.
Exactly.
I suffer this sometimes. So typically, we remove it. We put it again, and then you need this calibration. What you are saying that you have this automatic calibration, there is some kind of program that you launch, and the vehicle itself is just auto-calibrating, something like this, no?
Exactly. So the vehicle does these maneuvers that the maneuvers look basically like this, like what you have seen now. So it drives in circles of different diameter, and after about 10 minutes, it just it auto-calibrates. And
But
it has
do you do the calibration before or after the mapping?
Good question. So you do it after the mapping, because you need to have the map. So you need to have the map and localize on the map to be able to calibrate.
And how do you make the first mapping if it is not calibrated? I mean, it's like a wheel,
Yeah, like a loop.
Yeah.
So basically, for the mapping, the mapping uses only data from the laser, and so it doesn't care about where the laser is on the vehicle. No, it will just create the map regardless. And
we have one question, Damjan, in the chat. Is saying, do you need reflectors for this mapping?
No reflectors at all. So we just use raw laser data, which uses the natural features of the environment to localize.
And then we have, let's talk about calibration 1 second. We have another question is saying that in auto calibration, do you need more space even though if it is mapped?
How do you need the space that you need for auto calibration? That's actually a good question. So that can be a constraining factor. So you do need some free space, like you saw. So these maneuvers that can be seen here. So they do take up some space.
In any case, you will provide some kind of footprint or something, because if I have to calibrate, I need to know more or less what is the space.
The space that you need. Yeah, exactly. That's right. Yeah.
Okay, good.
Absolutely. So there is some actually working. There is some ways to maybe still optimize the space to really because right now you can't do it in an aisle. So if you just have, you need to have like a staging area free or something to do the calibration, which if it's a really big vehicle, it can be the problem. So we're working on something to do it in an aisle. But so right now it does require some space. Okay. And so after calibrating, the important thing is to check if the calibration has been successful and if the whole system is well tuned, the controller, so if the whole vehicle is accurate. And the way to do it is to approach the same point from two different directions and then check the relative error. So, ideally we would have a system that would tell us the exact truth, but these systems exist, but they are really expensive. as a next best thing, we measure relative positioning accuracy, and this is really something that comes up in applications very often. So it's much easier to make a vehicle that's always accurate when it always drives the same path. But if you need to approach the same point from two opposite directions, this is really when any inaccuracy in your calibration, in your control system, in your localization is going to show up. And this is a test. So when we say, when we claim to customers that our control system, that our navigation system is accurate up to less than 1 centimeter, this is what we mean, that the error when you make these relative positioning tests, that they're going to be at less than 1 centimeter apart. This is the...
We had this question, what is the accuracy of the localization? But let me tell you, it depends also a lot on the vehicle, because if the mechanics are not great, if there are not everything perfect from the vehicle, maybe in the tolerance we have some problems. Okay, but anyway,
yes.
If everything is good, as you said, this 1 centimeter. This is what you said.
Yes, absolutely. So it's not only mechanical; it's also like the low-level control loops, that the way they are tuned. There is a lot of things that you need to make sure are well tuned for the system to work well. So the next step after calibrating is so we made a map, we calibrated, and now we want to design the roadmap. So when we're designing the roadmap, typically we will start by let's say physically tagging a few positions a few key positions. So typically it will be, if you have a big a storage rack, for instance, we will check where the beginning of the rack is and where the end of the rack is. We will place the vehicle there. We will remember these points in the map, and then we can interpolate between these points. So we can generate points between these points at fixed distances. So I mean, this is a simple use case where we just interpolated one. But imagine if you have a long corridor with tens of pallet places, you would just tag the first one and the last one, and then you would interpolate in between. And then that will really save a lot of time.
Okay.
And then we.
Oh, excuse me. Go ahead.
And so then we place all the different types of we call them points of interest. So you can have pallet place. So then there is a pre-pallet node where the vehicle typically does some kind of preparation, like lifting the forks to prepare to go under the load, etc. And some normal waypoints, then a charging node, and we will connect all of them. So we have with our engineering tool, we support automatically connecting several nodes. So you just select several nodes, and you just click connect, and they all get connected together already in a reasonable roadmap. Of course, I mean, this is probably with a more complex setup. You will need to do some manual corrections, some adding some things and removing some things, but a lot of this is done automatically, so you don't need to draw every line. Furthermore, there is a built-in optimization procedure, because what's really important is that these curves are continuous, so that the vehicle can drive them without error. And so we have a built-in optimization procedure that optimizes the curves to ensure continuity between the nodes. Sometimes you do need to tune by hand if it's a complex space, or if you want to do a more complex maneuver. And in this case, we also the curves are modeled by high order polynomials, where the designer can manipulate the control points to get any shape of the curve that they want. So this is polynomials up to the 10th order.
Okay.
So you really have a lot of liberty in shaping the curves.
So basically, it is able to help you to draw these lines, okay, if they are curves or lines or whatever they are, but you also still have the flexibility to modify them. That is
Exactly.
Okay.
Exactly. So
it's
there are
important
drawn
because
up
when we
methods.
go to install, this is a lot of the job that has to be done on the field, and it requires quite a lot of time. Especially when imagine that we have a buffer with 100 position pallets, so mapping each point, etc. Not mapping. Routing, okay, all these nodes and all these things takes typically a lot of time.
Exactly. So this is what the part that we try to automate as much as possible, but still leaving the opportunity to fine tune it by hand.
Okay.
So the next thing, another important feature is that as you are changing the roadmap, sometimes, like you said, it's an iterative process where you make a roadmap, you try something, then you see that maybe the safety fields are not there. There is a problem with the safety fields that you need to adjust the route, and then you need to retest. And so in this case, we can have all the updates to the roadmap are transmitted live to the vehicle. So as you make a change, the vehicle already has this roadmap available, and you can just quickly iterate and test. This is something that working with some clients they had some custom in-house tools that didn't support this, and we're spending a lot of time making a change to the roadmap, downloading the roadmap to the vehicle, and then seeing that it doesn't work, and like this iteration. So we really try to make this iteration as smooth as fast as possible. So as you change it, it's live on the vehicle. And then and then you can monitor, and also during vehicle operation, you can monitor the execution of the curves and of the way that the vehicle is operating. And another thing that I want to know, so this prototype vehicle was built from the ground up by our team. I mean, we used a manual forklift base, and we did everything like sensor selection, sensor installation, mechanical conversion, everything. And because we started as a software company, we're like, we'll not get our hands dirty with hardware. We'll just do the software and let other people do the hardware. But we realized that, like you said before, everything is actually interconnected, so so very oftentimes, when we work with the client, we actually also help them. We always tell them you need the low level control loops need to be well tuned for the control, but sometimes they don't. Their idea of what a well tuned control loop is different from what we actually need. So we're also able to help them, with that to really have all the layers of the system working well, to have a whole system that's working, that's performing at a high level.
One question, Damjan. We see here a forklift, but do you support also other types of cinematics, for example, differential drive, other things, or is it something that you are developing? Or
no, absolutely, great question. So yes, we support any type of kinematics on 2D, so that's moving on a flat floor. This is actually something that we did a lot of research on, and so we do forklift like tricycle, differential drive, but also arbitrary number and configuration of wheels. Sometimes we'll have like 2 wheels that can steer and have traction. Sometimes you can have more, like 4 or even 8. And any configuration. So our control system, so both localization and path following, it applies to any configuration. So you just tell it where the wheels are, and it will know how to control the vehicle.
Okay, thank you.
And so one important thing. So this is really one thing that we invested a lot of research effort into. Oops, sorry. I want to show the video number 5. To really work with different kinematics, and also with all these kinematics to be super accurate. So we use a method based on model predictive control, which has a model of the vehicle. It optimizes, so it knows all the maneuvers the vehicle can make, and it chooses the optimal maneuver at every time step to get the most accurate following. And this is also something we've recently been granted the European patent for this method.
And what is this? What is the special, about this MPC control method? Why is so accurate?
So it has it takes care of several things. So it first of all it knows the dynamics of the steering. So it knows that the vehicle cannot steer immediately. So it's aware of the steering dynamics. It's aware of the whole kinematic configuration of the vehicle, and then it has some special adjustments to make sure when the vehicle is going more slowly, it knows that it can look further ahead. It has more time to calculate. When the vehicle is going faster, it has less time to do calculations. And also model predictive control is specific because it takes into account also actuator limits. So not only that the vehicle cannot steer instantly, but the velocity limits and the acceleration limits. So it takes all of this into account to achieve really good accuracy.
Okay.
Okay, so this is let's say so far maybe stays so this is standard stuff. This is, let's say, state of the art, but it can help deployment, but there is still the human robot interaction part that we're talking about that's challenging, right? So when a person leaves a pallet that the robot needs to pick up, a person is never going to be as accurate, or people sometimes leave things where they shouldn't. So, and the robot, as accurate as it is, in this setup, it is blind, so it doesn't see the laser, doesn't let it see. The laser just tells it where it is in the environment, but it doesn't really check where the pallet is, etc. So what we have been really working on intensively in the
you said that the human
year.
interface. You said that the human interface is a challenge, and you are politically correct because it's a nightmare.
Well, yeah, I guess you could also call it a nightmare. So this is a technology called semantic segmentation. It's an AI technique which lets the vehicle know for every pixel to what type of object this pixel belongs. So, for instance, it knows. So, and we encode this in color just for us people to visualize it more easily. So we see that the green is the floor, light yellow is an empty pallet, orange is the pallet face, dark yellow is a loaded pallet, green is a load, blue are other vehicles, etc. So this really provides sort of understanding, like a new level of understanding to the vehicle.
And so this is done with a different device, okay? Is a camera? What is that?
Yes. This is a camera. Of course, it needs a camera to do this. Absolutely, yeah. It cannot do this with a 2D laser.
No. But is a kind of add-on. And what is the typical application of this? Okay, I see you are segmenting the staff, person, pallet, etc. But what are the applications that you are implementing in the robot?
Well, excellent question. This is where what I'm actually coming to next. So there is the first one application is obstacle avoidance.
Okay, so you do optical obstacle avoidance thanks to this thanks to this segmentation.
Yes, exactly. So this is so with obstacle avoidance we use all the available data. We also use the safety lasers, but we also do use the camera. So we see we also, this is in this case also this is a depth camera. So in addition to the RGB, it also has a depth channel. So we also get coordinates of objects in the space. And so based on this, we can, for instance, see these forks, which are invisible typically to the navigation laser, and we can avoid the obstacle. Of course, avoiding the obstacle is not always a good idea, not always necessary, depending on where the vehicle is. So that's why you can define zones. You can see here it's indicated by the green rectangle, where you can say, okay, in this zone, the vehicle is allowed to avoid the obstacles. In some other zones, not, because this is also, as you know, an issue of safety regulations. Yeah. You know that you have in the environment, you have to see where the vehicle.
There is a lot of discussions about obstacle avoidance. Yes, no. I always say, who cares? I mean, it depends on the project itself. If you have this feature, better it is. Okay, if you have the possibility to avoid whenever it's feasible and it's safe, of course, better it is. So there is not a a net answer to yes or not. I mean, depends on the
Yeah, exactly.
application.
And
But
this also, I agree. I mean,
if you have it, it's better than not having it.
Exactly, of course. And I mean, so of course, the first thing, you tell to clients, you need to make sure that there is stuff, not stuff lying around. But then you have some clients who, for instance, they have like working 3 shifts, and sometimes there is nobody there in the facility, or no like technical personnel in the facility in the night shift, because night shift is a really a big problem for people. So if there is something left in the pathway, it's better that the vehicle avoid it than to you lose the whole shift of operation, right?
Okay.
And so the next application that we did based on this is adaptive pallet pickup. So this is again the human robot interaction challenge, which is like I said, what if the person left this pallet placed inaccurately? And so in this case, the vehicle can see it recognizes the pallet face, and it can estimate its pose, and can see that it cannot pick up the pallet from the default position that was remembered in the roadmap. So in this case, we allow the vehicle to replan its route and do a new approach to pick up. Which we will see right now, and you can see here in the top left corner. So it's the segmented image that the vehicle sees, and it replans the path at a bigger angle, and with this it's able to actually correctly pick up the pallet.
So it's very. I mean, it's when you put there is people putting pallets. It's clear the tolerance cannot be always perfect. We saw in the video that is in any case is quite slow. This movement. Okay. Is it possible to approach the pallet correctly on the first try? I mean, already knowing that is already not in the right position, or you have to go verify, go out, and go in.
So it depends. In this case, it also depends on the space you have. So if you have a lot of space to approach the pallet, then you can. But usually in warehouse, you never have a lot of space to approach the pallet. And then it also depends on the kinematics of the vehicle. So there are some vehicles. In this case, we're working with a standard tricycle vehicle, but there are some vehicles. A lot of manufacturers. Now we're at Logimat. A couple of weeks ago, a lot of manufacturers now have vehicles that are omnidirectional. An omnidirectional vehicle could correct immediately. So or if the vehicle had side shift on the forks, it could also maybe just move the forks to pick up. So there is different options for this different situations.
Okay, I just well, we went. This is the end of the presentation, but there's some question here. For example, what are the requirements? The requirements in terms of computing capacity for your solution? Because I guess you are providing the software. Okay, imagine that I want to produce a mobile robot. Is there a requirement in terms of computing? Yes, of computing capacity.
Yes. So with the first let's say the first part of our solution, which relies on lidar, we're really able to run it on some constrained industrial systems. So like a single core Pentium mobile processor at 1.6 gigahertz. So just a really constrained system. So it's not super. If you add more lidar, so if for instance if you want to localize with safety lidars and you have 2 or 3 of them, it becomes more computationally intensive. But typically it's something that is already there in most industrial systems that we have encountered so far. The other part, the part based on vision, for this you need GPU, so it relies on GPU processing, and so you need a special dedicated system for that. Yeah.
Mm-hmm. And do you have some kind of constraint in terms of hardware? Because we saw the navigation LiDAR, for example, okay, the safety scanners. Are you obliged to use some kind of brands or models, or you are agnostic from the sensor point of view?
No, we are completely sensor agnostic, and this is one thing that, for instance, where ROS is playing a big part, because so if you're using interfacing using ROS, it's already sensor agnosticity is already built in. You have a laser, and the laser has its interface. It has the data that it publishes. So you don't even technically our software doesn't even know what kind of laser is it's talking to. Of course, there are some application constraints. Obviously a laser with a bigger range and with a bigger update rate is better than a simpler laser. That depends on the size of the environment and other things. But from a software point of view, there is no constraints to the hardware that you can use.
Okay. Well, Damjan, I think that we just there are some other questions in the chat that we run out time. Anyways, I will send them the contact. I will send you the contact of Damjan. Mm-hmm. I will take these questions, and Damjan will also contact you and answer to you about these questions, mm-hmm. specific questions about I have an AGV that is long and etc. So very specific for today. But in any case, and I think I found very, very interesting your system, Damjan. Thank you for a part of your system. I think we learned how does everything work. That is fine always. So the mapping, calibration, everything, So very, very, very nice. Thank you. Let's say that for me it's finished. If you have something else to add, feel free. Otherwise, we just can close the webinar here.
Thank you. Appreciate it. So if people have any questions, please forward me the questions. I'll be really happy to answer and to connect with people on LinkedIn and contact. And because I like talking about AMRs and AGVs.
I know, sir. I saw you that you want to speak about technical stuff, very technical. Okay. Thank you, everybody. Thank you as usual. Thank you, everybody, for being here, for giving us your time to dedicate to AGV Network these webinars. Stay safe, and let's stay tuned also about the new initiative that in next month we have another webinar, a new one. So thank you for being here. Bye-bye.
Thank you. Bye-bye.